And we're ready to go. Alrighty, so this is going to be our exam 1 review for the midterm. And there's 20 multiple choice on this exam, 5 written problems. Those 5 roughly will cover the 5 weeks that we've been kind of going over physics topics. So you'll get one from each week, basically. So you get one kinematics problem, you'll get one buoyancy type problem, right? Stuff like that. And you'll get one maybe with Newton's second law, And so the exams are usually well spaced out with different concepts and topics, so everything is evenly covered. There's the good thing is that they rarely ever really go down for the questions about the last week's stuff. So buoyancy isn't like a huge thing you'll see. Hopefully, at least on my exam, I didn't see it too often, and on this practice exam, it isn't like a huge topic. Mostly, it's just going to be about the core first 4 weeks. So someone says the screen is blurry. Okay, I'm zoomed in now. Let me stop sharing and then reshare again. Hopefully that kind of fixes it. Okay, we good? Okay, cool. All right, so first off, I'm gonna start with problem number 2 here. Problem number 2, I got a couple DMs about this one. This one, I think the main mistake that a lot of people make is that they don't try to think about this using the kinematic equations, and they immediately try to go to the definitions of acceleration, velocity, stuff like that. So problem number 2 is car drives in a straight line with constant acceleration. It starts from rest at the origin at t equals 0, and then at t equals 10 seconds, the car is 100 meters from the origin, right? So at t equals t seconds, we have the car at 100 meters. That's its position at t equals 10 seconds. At t equals 0, it's at 0 meters, right? Now, another key part of the problem here is that we're starting from rest, right? So that indicates that our initial velocity is probably going to be 0 meters per second, right? Now, the question is to figure out how far the car is from the origin at t is equal to 20 seconds, right? So, equation that you want to use, how you want to relate things, well, first of all, I want to figure out what my delta x is, right? I want to figure out what the displacement is. Now, the problem refers to a constant acceleration. We're not quite aware of that yet. We have an initial velocity, right? And we have time values, 0 seconds, 10 seconds, 20 seconds, right? So we know that the displacement by the time we get to 10 seconds is 100 meters, right? And so we can use this equation, Vix plus half at squared, to help relate this known value, which is 100 meters by the time 10 seconds. T would be 10. Vi we know is 0. And then we can use that to figure out our constant acceleration, right? There's going to be acceleration throughout both time intervals, from 0 to 10, 10 to 20. That constant acceleration is going to be the same. Using that formula, right, once we get our acceleration, we can use it again to then figure out, after 20 seconds, what the displacement is going to be, right? So you have 100 meters is equal to Vix, and this is t, by the way, my bad. This should be Vxt next to it. And so this turns out to be 0, right, because we started off at rest, and so you're left with half at squared, right? Half at squared is what you're left with. And so you have 10 seconds as your time interval, right? And so that should give you like 50a, because you take 10 squared, that's 100. 100 divided by 2 is 50. 50a, 100 meters, right? That gives you an acceleration of 2 meters per second squared, right? Now we can use this same acceleration to then plug it in back into that same equation, Vix t plus half at squared, right? To then figure out what the displacement is after 20 seconds. So once again, our initial velocity is 0, right? We have half at squared. A is now 2, so 2 times 1/2 is 1. That cancels out, right? So then we're just left with t squared. Now t is 20 seconds, so then that gives us 20 squared, and that's 400. That's how we get the 400 here. Now, a lot of people have gotten 200. I think the mistake that they're making initially is trying to take what? I think I've seen people do like 100 meters divided by 10 seconds, right? So that'll give you like the velocity final or something like that, right? And then I think some people are trying to then take that value and figure out the acceleration, and they're ending up getting like I don't know, like around 1 meters per second squared, which if you do that route, that's what you get. You do get acceleration equal to 1 meters per second squared, which is incorrect, because the idea here is if you do that, if you take that 100 meters, for example, and divide it by 10 seconds, you're not getting the instantaneous velocity at t equals 10 seconds. When you want to figure out the velocity, right, delta v, it's delta x over delta t, right? Now, if you're finding it over this entire time interval, right, we're taking 100 meters divided by 10 seconds. That's giving us 10 meters per second, right? Now, you would think that that would be the instantaneous velocity, that velocity at that specific instant at t equals 10 seconds. But what that actually gives you is the average velocity over the entire interval, right? So that's the problem here that people are encountering. So I would say use this equation to help you relate what values you know. Don't try to calculate other values maybe that you think that you'll be able to get, right? Because some people, initially even me, I tried to figure out what the final velocity is here at t equals 10 seconds and then use that as my initial, right? Because then I can go from 10 to 20 with this being my initial. And so that's where people kind of go wrong. And so I would just say work with what you have. Don't try to figure out some other values. You have VI is equal to 0. You know your delta x. You know your time. Okay, what other values are missing? I still don't know what delta x is at 20. How can I figure that out? Well, they mentioned some kind of constant acceleration. Let me figure out what the acceleration is, then use that to kind of work backwards, use the equation again, and then be able to figure out the displacement at 20 seconds. Does that make sense for everyone? This one was a very popular question that I've gotten. Hopefully it does. Thumbs up? Okay, cool. Other than that problem, you can see here 1, 3, and 4 are kind of like real quick definition type problems, right? So they're asking you kind of the direction of velocity, acceleration, if you're speeding up, slowing down. So if you are aware of what it takes to speed up, what it takes to slow down, those problems should be hopefully pretty easy. And then this one is a straight up just kind of like a conversion problem, going from kilometers per hour to meters or furlongs per second, my bad. So that's kind of a straight conversion there. I think another problem I wanted to go over here, this one. So this one is another popular one, gave people a lot of trouble last semester too. Can you show the work for 4? This one up here? The furlong one? Yeah, so that one real quick is 1100 kilometers per hour, right? And so we know that a furlong is in meters, right? For we have this conversion factor here that a furlong is 201.168 meters, right? So we want to get it to a point where we're getting meters and then we can convert it to furlongs, right? So 1 kilometer is 1,000 meters, right? And then 1 meter, or my bad, not 1 meter, 201.168 meters is 1 furlong, right? And then from that furlong, right, we have furlongs on top, which is what we want, right? And we want seconds now on the bottom. So then you have hours, right? 1 hour is 60 minutes. And then 1 minute is 60 seconds. Sound good? Cool. All right. So reasoning of 3. Okay. Consider an object which is moving at constant speed while moving in a circle, where a is the acceleration of the object. Which one of the following statements is true? So, let me actually read that again. Consider an object which is moving at constant speed while moving in a circle. A is the acceleration of the object. Which of the following statements is true? A is not constant, and the reason why is if you're going in a circle, think about it, right? Well, that's kind of an oval, but who gives? All right. So for acceleration in kind of like a circular type motion, right, which is what you guys are going to go over actually this week, is the idea that acceleration is, yeah, absolutely right. acceleration is going to be constantly changing. It's going to be pointing radially inward towards the center of the circle, right? That's the idea for what we call centripetal acceleration. So at any point in the circle here, it's always going to be pointing towards the center. The acceleration always going to be pointing towards the center. So like if you want to think about it, right, this is technically like, right, so if I look at here, acceleration pointing north, right? Down here, or up here actually, it's pointing south, for example. So it could very well be 4 meters per second squared, but if we're, for example, assigning like a y-axis and an x-axis, right, this right here, at this point, acceleration would be 4 meters per second squared in the positive y direction. Up here, it would be pointing inwards again towards the center of the circle, and that would give you negative 4 meters per second squared relative to the y-axis. And so that's why just the value itself is not constant for acceleration, but the magnitude is, because you're constantly changing direction throughout that circular type turn and motion. That's what causes you to have an inconstant acceleration. Yep. Acceleration is not zero for like a circle type motion, right? The only time that I think you guys might be thinking about acceleration would be zero is that if you have like a v versus t graph, right? And you kind of have it curved like this. Well, at this point right here, if you've taken calculus, you'd know that the derivative of a velocity versus time curve should give you the acceleration, right? Now, if you haven't taken calculus, it's basically, that just means that if you take the slope of the tangent line here, right, or here, for example, that'll give you the acceleration value. So the slope here at the peak, where the velocity versus time graph is flat, whenever the velocity versus time graph is flat, right, that's a horizontal slope, and a horizontal slope is zero, and that at that point you would have a zero acceleration. Yeah, and Victoria, yeah, the magnitude is the same, so it could be very well 4 meters per second squared throughout the entire circle. It's just that there's a constantly changing direction, and so that's why it's not constant. Make sense? Okay, cool. I'll try to move on first to like the ones that I feel like are the most important, and then I'll try and address as many ones as we can for the multiple choice, the other ones. So we have here number 10, an object travels non-uniformly along the x-axis. This object's position versus time graph is shown to the right. Determine approximately the object's final speed, right? So this is what I like to call some bullshit right here, because the way to figure it out is kind of stupid, and it can confuse a lot of people, and it certainly confused me when we took the practice exam in 131. And it's I don't know. Anyway, so you have your position versus time, right? So when I was talking earlier about velocity versus time, if you find the slope of velocity versus time graph, slope of v versus t, that's going to give you acceleration. Likewise, slope of x versus t is going to give you velocity. The reason why is, if you think about it, slope is like y2 minus y1, x2, or divided by x2 minus x1. So you take your y variable, the change in your y variable over your change in your x variable, right? So in this case, your y variable is position, that's x variable is time, that's t. So x divided by time, that gives you velocity. Velocity divided by time, that gives you acceleration. So that's kind of the relationship between slope and the graphs and stuff. So with that being said, we have position versus time, right? So with this position versus time graph, if we take the slope at 6 seconds, the slope of the tangent line right there, that should give us what this final speed is, right? Or at least in this case, if you think about it, right, since this is a negative slope, it should give us a negative velocity. And if we just take the magnitude of that, take the absolute value, that should give us our speed. So this might be like negative 3 meters per second, right? If you were to calculate the slope out. But since they're wanting speed, and speed is the magnitude of velocity, it's without direction, we just take that negative sign basically out, and then you are ending up with whatever, 3 meters per second, whatever, you know. Now, the issue with this here is that if you try to estimate this, let's say you're looking at 5 seconds here, and this, let's say this is about like what, maybe 0.8, because this is 1 right here. Let's say this is 0.8. So let me write that down. So at 5 seconds, we have 0.8 meters, right? And then maybe at 6 seconds, we have, 6 seconds, we have what? -1 meters. If we were to try to find the slope out from this, we get kind of a conflicting answer. I think you get more close to like 1.3 meters per second or something like that. I think if you do -1 minus the 0.8 there, you get -1.8. Oops. -1.8. You divide it by 1, because you do 6 seconds minus 5 seconds. You should get a slope of -1.8 there, which, if you estimate it right, and obviously if we take the absolute value, we should get a speed of maybe 1.3. But the issue with that is it's unfortunately the wrong answer, right? Now, we were kind of discussing about the best way to go over this and figure this out. And so my idea, personally, I think the easiest way to go about a type of problem like this is to instead look at the shape of the slope. What does the slope look like? Like if we were to kind of draw out the slope here like that, I want to look at that shape right there, that incline. Now, 1.3 meters per second, what does that look like, right? So if I were to draw it here, from 0 to 1, that's 1 second, right? And then from 0 to 1 meter, or -1 meter, it should look like this, right? Now, if we were to kind of grab it, transpose it on to that, doesn't look quite the same, right? So then you can immediately kind of think about it and say, well, okay, it's probably not one of these 1.3, -1.3 type answers here. So, okay, I see some questions here, my bad. Yeah, there's a blank PDF of the practice exam in the folder for your professor's Blackboard page. Practice exams, our answer choices are slightly different. 4, -4, oh, okay, I see. That's fine. It's still going to be kind of, I mean, I'm assuming the problem's hopefully the same. I don't know why the copy is different here. Anyway, yeah, 4, -4, 2, -2, -1. They probably just removed the whole 0.6 stuff because that was just throwing people off. So this is, yeah, this would be like your -4 answers. These would be -2, like -1. So it's the same kind of group. But hopefully you'll kind of get the idea of where I'm going here in a sec. So since I already said that this incline here, if I transposed it, it didn't look kind of like the same incline here on this section of the graph, what I'm going to do is then try out, okay, well, let's see what 2.6 meters per second looks like. So 2.6 maybe is about like that, right? So if I drag it, transpose it, we're getting closer, relatively. Now, if I take like 4 meters per second, well, that's going to be crazy. That's going to be really very steep, right? And so if you look at it, 2 should be the closest one. Because if I try to transpose this one, this is really, really steep. 1 was a little too shallow. 4 is a little too steep. 2 is just right. And I think especially they probably removed that 0.6, right? Because that just made things a little bit more difficult. And so if you just do 2 and you transpose it, it's darn near a perfect fit. So that's kind of how I went about solving this. Just take the slope at that specific point and then try and relate it to your own kind of drawing here to show that, yes, we covered 2 meters in 1 second, because this is 1 second here. This is 2 meters down here. Draw what it looks like, that coverage, and then kind of try and transpose it here and see if it looks about the same. Now, you might be wondering, like, okay, well, why can't we just like calculate the slope and figure out like why is it not quite working? Now, the issue is you're trying to find the slope at exactly 6 seconds. If you try to take a value here and a value there, and you try to figure out the slope, you'll get a slope value that's more close to a value that's like maybe 5.5 or something. So it's really difficult to estimate exactly what the slope is at 6 seconds. That's the issue. And so if you can try and relate the answer options and try to say like, okay, well, what distance is covered in that 1 second, try to relate the length there. covered in that same time interval and see if it matches the slope at 6 seconds. And you can see that 2 meters per second most closely matches that one. And yes, the session is recorded. It'll be uploaded both on YouTube and Google Drive. And it'll be available like within an hour or so after the session. Now, okay, so someone said it's positive because it's going in the negative direction. It has a negative slope. So wait, hold up. What do you mean exactly about that? It's positive and it's going in the negative direction. If it has a negative slope on a position versus time graph, you have a negative velocity. Now, on this position versus time graph, anything above the x-axis here, that's going to be a positive position. Anything below is a negative position. So like here, in this little interval here, I would be, okay, if we said from here to here, right, that would be me still in the eastward direction, but moving left, basically. It's kind of weird. And then this right here, this interval, would be moving in the leftward west direction and with a negative velocity, so I'm still moving left. Yeah, the answer should be positive because you're taking the magnitude of what you're seeing here. So if you have a negative slope is going to give you a negative velocity. And so speed is velocity with a direct, oh, my bad. Velocity is speed with a direction. So we just take the magnitude of the slope here. So if the slope is negative, we should make it positive in order to get the speed. Because all that's saying, a negative slope is just saying that, oh, I might be traveling 2 meters per second south or 2 meters per second west or something. So you just have to take the absolute value to adjust that and give you speed. That's all. Does that make sense? Yeah. Yeah, speed is going to be the absolute value of your velocity. So if I'm traveling 10 meters per second, that's my speed. Now I could be going negative 10 meters per second. That would indicate maybe in the negative x direction, the negative y direction. So velocity is just adding a sign to your speed, basically. Yep. Yeah, that one was a doozy to figure out just because the slope stuff was just horrible because we had to like really kind of squint and choose the values as close as possible as we could to match the slope. And so I just think that if you just draw, like if they gave you 2 meters per second, okay, well, 2 meters per second, here's 1 second, this is 2 meters covered. Does that slope match kind of the slope at 6 seconds? Yeah, relatively. So I'm going with that. I think that would be the best way to go about a similar problem if, you know, it's really difficult to kind of estimate it because the graph really ends at 6 right here. Maybe if they extrapolate it a little bit, might make it a little bit easier to figure out. You might get an answer that's more close, more representative of what the right answer is. But yeah, if I doubt they're going to pull something like, I don't want to say stupid like this because frankly, this was just the answers were just too close and it was just very ambiguous sometimes. So, but I think you would be expected to figure out velocity from a position versus time graph, acceleration from a velocity versus time graph. So interpreting graphs is just very, very important. Now, if everyone's good with 10, then we can move on to 12 here, which I've singled out as well. Now 12, once again, it's an issue because, well, they don't even give you the coefficient or the drag coefficient. So this is kind of like a typo. And oh, my bad, not drag coefficient. I'm thinking about another problem later on. Coefficient of friction here doesn't add up. That's what I meant. Coefficient of friction doesn't add up here. So let me kind of go over it real quick. So this says a 12 kilogram block is sliding over a horizontal surface with which it has a coefficient of friction, mu is equal to 0.80. Now the block is slowing down at a rate of 2.5 meters per second squared. What is the magnitude of the force of friction on the block? So, oh, the answer that you guys have is 60 newtons? That's weird. Oh, you guys had mu as 0.5. Well, I don't know if I just have like an outdated practice exam or if I just downloaded the wrong one or what happened, but okay, sure. I mean, we can go with a mu of 0.5. Let's do that. That's fine. No worries. So mu of 0.5, right? We're trying to figure out the force of friction. So if you're sliding, what type of friction do you have? Yeah, excellent. Kinetic, right? Kinetic friction. Now, what is that kinetic friction equal to? There's a specific equation to figure out kinetic friction here. Yeah, absolutely. And a couple, yeah, you're absolutely right. And a couple other people got it too. So yeah, you take the coefficient of friction times your normal force, right? Now, you have this coefficient of friction 0.5, right? Normal force here, since it's just a block sliding over a horizontal surface, so it just kind of looks like this. Block, horizontal surface. So you have gravity pointing downwards, normal force pointing upwards, right? And so since this block isn't levitating, this isn't Harry Potter, right? So we're not levitating this block or anything like that. It's just moving solely over the horizontal x-axis. Then your normal force should cancel out with your gravity. They should be equal and opposite to each other, right? So if the block is 12 kilograms, hopefully you guys have it 12 kilograms too, unless they changed up the values for that too. But let's say the block is 12 kilograms, right? Then force of gravity, Fg is equal to mg. We just take 12 kilograms times 10 meters per second squared. That's 120 newtons, right? So our normal force should be 120. So you should take like 0.5 times 120, and yeah, that should give you 60 newtons. That'd be the easiest, quickest way to figure it out, in my opinion. Now, alternatively, what you can do is use this acceleration here. Well, if the object is sliding, right, in the x direction, we don't have any indication of any push force or anything like that. So we just have Fk prime here, kinetic friction acting on it. So you can also set up a F net equation, right? And realize that, okay, F net is equal to max, and that's equal to kinetic friction. That's the only thing that's kind of acting on the object at this point, right? So we know that the 12 kilogram block, that's the mass. Acceleration is 2.5. If you're to do that, that's where you get the 30 newtons for my problem here, right? The reason why I kind of put that the coefficient doesn't make sense is that if you take that 0.80 times, so remember we did mu Fn earlier? If you take 0.80 times the normal force, which was 120, you would get 96 newtons. And so I'm guessing what they did is then they just adjusted this value and I guess maybe adjusted the acceleration or whatever or something to make things a little bit easier. But did you guys also have 2.5 meters per second squared for your acceleration for this problem, or did you have a different acceleration, or did they just not give you acceleration at all? Oh, they gave you 2.5 as well? Okay, well then that throws things off a little bit then. That's weird. Well, I mean, both should absolutely work. There shouldn't be any doubt as to why either of them would work. The issue here is that I guess their acceleration values don't match up. And I checked this like a billion times. I even looked stuff up online to make sure that I wasn't going insane. And the coefficient just doesn't match up. Like, the only force that we have acting in the x direction should be the kinetic friction. So kinetic friction should be equal to your mass times acceleration. And then at the same time, that kinetic friction force should also be equal to your mu times your normal force. Either way should work. It's just that I guess they just messed up the values here for the acceleration and the coefficient of friction not adding up to each other or being level with one another in order to make both methods give you the same answer. So either method is absolutely correct. Don't be worried about picking one or the other. The exam won't have this type of typo, but like the reason why I just hate these practice exams because these typos have been here for like the past 3 or 4 semesters at least, and they've like haven't been fixed. So, I mean, yeah, go ahead. Yeah, like I said, either method is supposed to work. It's just that they haven't assigned the proper values to make them equal to one another. Because you get 30 for one and you get 60 for the other one. So like there's something that they just either have to adjust their acceleration value or they have to adjust their mu value in order for both answers to be correct. But by theoretical physics right here, the concept should work out to where either method works. And I've checked a billion times online that with similar problems, and they're all saying the same thing, and I'm not crazy. So yeah, if you do the first method on the exam, you should be able to get the correct answer. Yes, I don't foresee them like having that ambiguity on the question. Exam is usually very, very straightforward. There's almost always just one way to figure things out. Like I said, the practice exams, they're like there to kind of help you, right? I feel like they might just put a little bit more effort into making a quality exam than they do the practice exam. There's like, just be prepared for the rest of the practice exams to have like 5 or 6 different typos at least. So just be wary of that because it's like the most annoying thing in the world. And it's just like, okay, if you make a mistake, just please fix it, right? For the next couple of years, so I don't have to like question my physics knowledge afterwards. But yeah, either method is 100% correct. And I think I would say to be safe, I would probably still go with the mu fn method because that's just more straightforward. And that takes this value times the normal force and you're good there. But yeah, like I said, either method works. So hopefully that makes sense to clear things up there. But yeah. Are we all good for that problem there? Yes, okay. Other than that, here's the one that I was talking about where there's a missing drag coefficient. Is this the same problem that you guys have for 16? Hopefully it is. It's a 2 kilogram cube, which is 10 centimeters on each side, falls out of a plane. Yeah, I mean, answer is 82, 81. It's like, they still don't give you the drag coefficient, I'm assuming. Or at least, I mean, that would be funny if they just changed up what the answer value is without giving you a drag coefficient. Oh, okay. Well, I take back everything I said about the professors. Okay, cool. All right, so drag coefficient is 0.5. Right, any other information missing, or am I good to go then? Because I have density of air is 1.2 kilograms per meter cubed, and the mass of the cube here in the cross-sectional area. Okay, cool. So 2 kilogram cube, 10 centimeters on each side falls out of plane. Assuming that one cube side faces directly downwards, estimate the terminal speed of the cube. Density of air is 1.2 kilograms per meter cubed. So if you watched my previous session about drag, buoyancy, and all that, terminal speed, terminal refers to final, right? Terminating, axon terminal, right? It's the final piece, the ending, right? So terminal speed will refer to the final speed, the maximum speed that you'll be able to reach, right? Same for terminal velocity as well. You'll hear that in a lot of scientific shows. If you watch like The Flash or if you watch Star Trek, whatever, you'll hear terminal speed, terminal velocity maybe often or something. So with terminal speed, that terminal speed, terminal velocity is reached when you have your drag force equal to all other forces in that same axis. So in this case, if a cube is falling out of a plane, everything is along the y-axis. So you have this cube right here. Drag is acting against it, kind of like a friction force, right? Air resistance. And you have gravity pulling it downwards, right? So terminal speed is reached when F drag is equal to the other forces along the same axis, and the other forces along the same axis are gravity. So F drag equal to gravity. That should give us our terminal speed, or that's when our terminal speed would occur. So with that being said, F drag is equal to Fg here. We know that that's when the terminal speed occurs, right? And then we know that F drag is equal to half times the drag coefficient times the density of the fluid times area times velocity or speed squared, right? And then that's equal to mg. So using that, we are able to plug in drag coefficient, that's 0.5, density of air is 1.2 kilograms per meter cubed. Area would just be the cross-sectional area of the cube. And so the cross-sectional area, when they say that the cube, one cube side faces directly down, that cube side that's facing directly down, that's feeling that air resistance directly, that's going to be your cross-sectional area. And so 10 centimeters on each side, a cube, so just 10 times 10, that's 100, right? 100 centimeters squared there for your area. Now, you would have to adjust this 10 centimeters and convert it to meters to match up with the density of air there. Yep. So that would be the one adjustment that you would have to make to that value there. So you take half times 0.5 times 1.2 kilograms per meter cubed, right? Let me move this over a bit. And then you take that times the area, which is 10 centimeters. I'll just put 10 centimeters. Oh, my bad. 100 centimeters squared. Convert that to meters squared. Put that here, right? Times your terminal speed squared. And then you have your mass, 2 kilograms, times your gravity, 10 meters per second squared. And then you can kind of solve to figure out your terminal speed. 0.5 is your drag coefficient. They never gave us the drag coefficient on my document, but I'm guessing on your guys' document you should have the 0.5 for your drag coefficient there. But yeah, sound good for the explanation for this problem here? Let me check my work here and make sure that everything checks out. Yeah, so do you want me to do the conversion out, or do you want to just tell me? Do you want me to just tell you what it is? Because I mean, 100 square centimeters is 0.01 square meters, and so you can figure that out doing. So we take, this is 100 centimeters squared, right? Just do there are 100 centimeters in 1 meter, right? And you want to have this be meters squared, right? So what you do is just take the square root of that part in order to get meters squared, because then you'll have centimeters squared, and this would be meters squared. Centimeters squared would cancel out, and so that's how you get your meter squared. And I believe it should be 0.01 square meters, I believe. Yeah, 0.01 as far as I'm concerned. Is that good there for the, yeah, so if you just take that, let me make sure that the value here, everything checks out. So 0.5 times 0.5 times 1.2 times 0.01, 0.03, okay. Yeah, roughly should be about that 82 meters per second. Sound good for 16? Cool. All right. Now, 17, fairly certain this is a mistake as well. I don't know if they corrected it on your guys' version of your document. I mean, I hope so, but do you see anything different here? Any additional information given for 17? What 2 meters per second squared where? Yeah, 82 or something like that. Yeah, because I think you guys have 82 and I just have 81 here. So it's just, I guess it's an older document. 26. Okay. Has anybody else checked? Like maybe I missed something. Have you guys checked my work there? See if everything makes sense. Yeah, at 82. And you used like the same equation setup that I did, right? Okay. So, I mean, you should have half times 0.5 for your drag coefficient, times 1.2 kilograms per meter cubed for your fluid density, times your cross-sectional area, which should be 0.01 meters squared, times your terminal speed squared, and that should be equal to 20 newtons on the right. So if you divide 20 by all the other values on the left, and then you take the square root, that's how you should get your terminal speed. So it's kilograms per meter cubed, yeah, and that's the density. But it shouldn't matter, you just plug in 1.2. I tell you what, let me just go through as many problems as I can because I just want to make sure that we're covering as much stuff as possible for everyone. And let's just kind of put that aside for now, and I'll come back to it later if you're still having issues. But or if I'm not able to get to it now, just DM me and I'll help you out. But I don't think radians should have anything to do with this stuff. But yeah. I'll just move on to 17 for now, and just I'll address number 16 for you later. But yeah, if you might have just kind of plugged something in incorrectly, forgot to take the square root or something. So I just checked just to be sure. But as far as I'm concerned, and for the other students as well, I think that should be the correct setup. So I just double check your calculations just to be sure. But for 17. It says, takes a force of 10 newtons to stretch a given spring to double its original length. How much force does it take to compress that same spring to half its original length? So we know that the force here for the spring, right, it should be the spring force, so F equals kx, right? That's our spring force. So if we know that the spring force is 10 newtons to stretch a given spring to double its original length. So what I like to do, this is inefficient to a certain extent, but it just keeps me like sane and in check, and that I'm making sure that I'm doing the right stuff during the exam. I just like to plug in a very small value just to make sure that I'm like doing the math properly. Because you'll see a lot of these problems where like, oh, if I double this length, or if I double the velocity, like what happens to the acceleration, or what happens to this or that, right? So you'll see a lot of these types of problems, and this will happen too in Physics 132. You'll see a lot of these types of problems where you have to double or triple or make some adjustment to one variable and figure out the change in the other variable. So with that being said, if I were to start off, for example, with an original length of 2, right, and I wanted to double that to 4, for example, right, well, then I know that 10 newtons allows me to jump to that double length, right, to 4. And so that gives me a K, for example, of 2.5, right? Now that I figured out my K, I have F equals 2.5x, right? So now how about if I compress the same spring to half its original length? Well, we said the original length was 2, right? So half that original length should be 1. So if I multiply 2.5 times 1, I should be getting 2.5. And so this answer right here is a typo. This is a mistake. I believe it should be 2.5 newtons. Does that sound about right? I mean, that's how I did it. I figured like I put in numbers and stuff just to make sure. Did you guys find the same thing when you were doing number 17? Yeah, no, these practice exams always make me think like I'm just on something else when I'm solving them. Like I have to double, triple check that I'm not like doing anything wrong. And so there's also this like superiority or inferiority complex, because you're like, well, the professors have to be right, and so you try to figure out a way to make them right, but in the end, it's just wrong. So, yeah, go ahead. I didn't get 5. I didn't get 5. I got 2.5. This should be a typo. This is a mistake. Yeah. Because if you were to plug in, like if you were to say original length was 2, right? If I want to double it, it was 4. Well, 4 meters, for example, or 4 centimeters or whatever, is going to occur at 10 newtons. And so then my K, my spring constant, is 2.5. If I plug that into an equation, F equals 2.5x, well, if I have half the original length, that's just 1. So 2.5 times 1 is 2.5. But yeah, that's 17. That is it for the problems that I thought were just tough or just mad stupid, to be honest. But other than that, any specific problems for the multiple choice you guys have in mind that you'd like to go over, or do you guys just want to like jump to the written stuff? So we have number 18, we have number 9 as well. Let's see here. If you don't mind, I can do number 9 real quick, because that one is just like very, very, just, very quick. And so then I'll jump back though to number 18, because number 18 is a little bit more difficult and it kind of applies the buoyancy stuff. But yeah, number 9, I'll square that away and I'll come back to you, Matthew. Sound good? And yeah, the exam does really take 2 hours, or at least the length is 2 hours. You don't necessarily have to take up the whole time. I know some like geniuses that were able to finish in like 45 minutes, an hour. But it just kind of depends. Regardless of my ability, I don't like to just finish things early. I'd like to take my time, be thorough, make sure I have everything correct, because God knows I'll make a stupid mistake here or there. So, and yeah, let me see what 13 is. 13, that's really quick too. Okay, so I'll just jump to number 9 for a sec. So it says, when Abner weighs himself at home in the morning, he sees that he weighs 150 pounds. Abner carries his scale with him to an office building. While taking the elevator up to the top floor, he stands on the scale and notices that the scale reads 120 pounds. What was the elevator's y acceleration when he read the scale? So when he weighs himself at home, he's not in an elevator unless he's rich, okay? So for the numbers here, okay, what numbers do you guys have? $400 for the second part. Okay, no worries. And then are your acceleration values the same? Okay, cool. No worries. So here, when he's weighing himself at home, like I said, unless he has an elevator at home, he's just a normal guy, all right? So he's weighing himself. He's 500 pounds, I guess, which is, whoa. Why would they change that? That's just such a... Why? There's no reason for that. Okay, I guess he's 500 pounds. So nothing against that. I just want to make that clear. It's just I find that to be okay. Cool. I was about to say like 500 pounds. Like that's like for why? Okay, 500 newtons, 400 newtons. Fair enough. That actually makes it easier. Okay, cool. So we have 500, 400, right? When he's weighing at home, he's stepping on the scale. That should give him his actual weight, right? His actual weight of 500 newtons. So when we're talking about weight, what does that refer to? mg, right? Force of gravity. So your force of gravity should be 500 newtons, right? Now, when he's in that elevator, right? If you remember those elevator type problems, and you notice the scale reads 400 newtons, right? What is that referring to? I mean, he's still like trying to measure his weight, but it isn't necessarily the force of gravity. What do we call it? Yep, that's the one. Apparent weight, right? So apparent weight refers to the contact forces, right? So if he's on that elevator, he's stepping on the scale, right? You have normal force and you have mg, or force of gravity, right? Now, what's your contact force here? Yeah, normal force, exactly, right? Normal force, that's the force that comes from a contact surface, basically. That's the idea. So we have normal force here, right? So normal force is your apparent weight because it's the contact force, or essentially apparent weight is the sum of all contact forces, and so the only contact force here is normal force. So therefore, this is equal to normal force, right? Now, it says that he has what is it? While taking the elevator up to the top floor, he stands on the scale. Okay. Now it's asking, what's the elevator's y acceleration? So if the elevator is moving upwards, right? There's a what upwards? What do we have? What's going on upwards? There should be a net blank. Net positive what? What are we talking about here? Net positive gravity, net positive force. Yeah, there we go. Net positive force, right? So there should be an F net positive, right? And that elevator should have some kind of positive acceleration, right? And that acceleration is technically transferred to the person in the elevator, right? So they have mass times acceleration. And the mass here isn't the mass of the elevator. We're referring to just the mass of the person, right? It's what they're feeling. That's what we're concerned with. They just feel the overall acceleration from the elevator. So if we were to write an F net equation, we have Fn minus Fg, right? That's what? 400 minus 500 newtons. So that should give us negative, let me try and write this here. F net is equal to MA. That should give us negative 100 newtons, right? And so going back now, we need to find out our acceleration. We can figure out our mass, right? Because we know that the weight is 500 newtons. So we know that this is equal to Fg, this is equal to mg, right? G is 10 meters per second squared. If we divide 10 over, we should get a mass of 50 pounds, I believe. Or 50 kilograms, my bad. 50 kilograms. I was going over by the old values. I wrote pounds again. Okay, 50 kilograms, right? So if we can plug that in, 50A is equal to negative 100. Divide 50 over, you should get A is equal to negative 2 meters per second squared. And so, in this case, actually, I kind of made a mistake. I made an assumption saying that there's a net force upwards, technically, which is a mistake there just because now we're looking at this net force being negative 100 newtons. And that means that the force of gravity, as you can see, is overwhelming the normal force. So force of gravity is actually greater here than the normal force. And what that means is then, since we have that negative acceleration, right, it means that, yeah, sure, it's still moving upwards maybe, but maybe like it's slowing down or something, right? Because you're moving upwards. It says the elevator's taking it up to the top floor. It's just that force of gravity is greater, right? So that's all. Make sense? Cool. All right. 9, and then we had 13 is very, very quick. It says frog is sitting at rest on a slope. Angle of the slope is 30 degrees above the horizontal. Coefficient of friction is mu equals 1. What is true about the magnitude of the force of static friction? Well, we mentioned earlier that, I guess not earlier today, but in general, like if you've been to my sessions, if you've been watching the videos, you know that static friction force, right, is at its maximum, right? The static friction force, it's a range. It's a variable force. Right? It can increase over time. And it's less than or equal to mu times Fn, right? It only reaches that maximum. It only equals mu Fn if the object is about to slip. Static friction force is kind of like your grippy force, quote unquote, right? It's the force that helps propel you forward if you're walking. It's the force that keeps tires from slipping on a road, right? It gives you some grip, right? So think about static friction force as gripping, preventing you from slipping, right? And so in that case, there's no indication that the frog is about to slip. There's no indication that this frog is about to like fall down or anything. So we shouldn't see a maximum. And the static friction force is never greater than your mu Fn here, based solely on the definition of static friction force as, less than or equal to mu Fn. So C is extraneous. That shouldn't even be an option. Equal to only occurs when it's at a maximum. And less than here would just occur pretty much any time else where it's not slipping or that it's not about to slip. Does that make sense for number 13? Yeah. we'll hop to 14, but I will take care of 18 first because another student had asked for 18 before. I just want to make sure that I'm addressing everyone. But we have a rod of length L is equal to 30 centimeters, floats vertically in water. Density is 1 gram per centimeter cubed. As shown in the figure to the right, if it has a cross-sectional area of 1 centimeter squared and its density is 0.6 grams per centimeter cubed, what length LW is submerged, right? So thing is for this one, right, this rod is floating, right? It's not completely sinking, right? So what does it mean when an object floats relative to forces acting on it? Because usually we try to think about two forces in particular when we're looking at. So if it's floating, the forces are equal, right? If it's floating, the forces are equal. Force buoyancy is equal to force of gravity, right? But, I mean, technically I see some people are looking at density of the object, density of the fluid. So if it's floating, then yes, the density of the fluid is greater than the density of the object, absolutely. The thing here is that your overall force of buoyancy is equal to force of gravity. And then within those forces, when you're doing density and volume, you're calculating those things out. Volume of the object, the overall volume here, let's say that's like, I don't know, 16 centimeters cubed or something, right? That's the volume of the object. Volume of the object is 16 centimeters cubed, for example. Now the volume displaced, the volume of the fluid displaced might only be like 9 centimeters cubed, for example, right? And so if PF is greater than PO, I just like to say P and instead of rho, it just makes it easier. I just like to say fancy P, fancy P, yeah. So I'll just keep referring to this as P from now on. So P for your density, right? If PF is greater than PO, right? Then in order for them to be equal, your force of buoyancy and your force of gravity, then in this case, your volume of your object is greater than, well, actually, let me kind of show you this way. So PF greater than PO, and so your volume of your object is greater than the volume displaced. So you see how there's like, they kind of cancel each other out? And so, the STEM gods are coming for you. Yeah, I mean, I'm not one for Greek letters. I know them, but I don't know. Sometimes, like, especially once you get to like pressure and density and stuff like that, there's so many like P looking structures, pressure, density, and it just gets confusing. So I'm just like fancy P, that's my rho, that's my density, and then capital P is my pressure. But that's a whole nother issue. That's a couple weeks from now. Anyway, hopefully you can see that your force of buoyancy should be equal to your force of gravity because the thing is floating basically, right? It's not sinking. And so in this case, since your force of buoyancy is equal to force of gravity, your density of the fluid is greater than density of the object. Volume of the object should be greater than the volume displaced. Now, that being said, right, we can kind of set things up here where we know that the force of buoyancy, this is really important, force of buoyancy is only looking at values relative to the fluid. So force of buoyancy factors in the density of the fluid, the volume of the fluid displaced, and gravity, right? Force of gravity looks at the properties pertaining to the object, right? So we have density of object, volume of object, gravity, right? Now, for the density of the rod, we know that's 0.6 grams per centimeter cubed. Density of water is 1 gram, so we have this value and we have this value, and this value is pretty much going to be canceled out anyway because they're the same. You can still factor them in the equation if you want to. But now we're looking at volume displaced and volume of object, right? So they gave you length values, they didn't give you volume, right? So you know that there's a cross-sectional area of 1 centimeter squared, and there's a length of 30, right? So what does volume equal? If we were to take a volume, like imagine this is a rectangular prism, right? how'd you take the volume of that from the values given here? Yeah, length times width times height, right? And so they gave us length, and the width times height is already given to us as the cross-sectional area of 1 centimeter squared, right? So area is now equal to length times the, no, I don't want to say, oh my bad, volume. Volume is equal to the length times the cross-sectional area, right? And so in that case, we can kind of plug in these values here. So we have fancy P, and we have the volume displaced. That's going to be the length of the rod, or the length of the water displaced, right, times the cross-sectional area, which is that 1 centimeter squared, and that's what times gravity, right? And then the other side is the density. Let me actually go ahead and plug in values directly. So this is 1 grams per centimeter cubed, and then this is what, 0.6 grams per centimeter cubed. Cross-sectional area just means like if we were to, if we were the water looking up, right, we don't see a rod. We just see the bottom face of the rod. And so that bottom face is just the square side, right? And so cross-sectional area, why they say it's cross, right? So if you were to cut this thing in half, the surface that you would see is just a square. That's the idea when we're talking about cross-sectional area. And so length of the rod now, right, because we're looking at the properties of the object, right? We're looking at the length of the whole rod, big L right here. So that's 30 centimeters. And then we can multiply that by the cross-sectional area, which is 1 centimeters squared, and then multiplied by gravity. Like I said, when you're plugging into your calculator, gravity doesn't even factor in at this point because they're the same, so there's no point in putting them together. It'll just add more values to your calculation and throw things off. And so, yeah, I mean, once you get that, you can finally figure out your length that is submerged. And that should be, if you do 0.6 times 30 times 10 here, divide that by, well, 1, 1, and 10, right? We should be good to go, and you should get 18 centimeters. Sound good? Yep, okay. Now, I think someone had another problem. They had 14, right? Consider the 3 identical blocks on identical surfaces, each subject to an external 10 Newton force directed as shown to the figure to the right. From smallest to largest, rank the magnitude of the normal forces exerted on the blocks by the surfaces. So I want to think about these forces here as like maybe some tension forces, like some pulling up or to the right or something, right? So if I'm looking at what forces are acting here, I have normal force, I have force of gravity, and I have this 10 Newton force like this. Let's say Ft, right? This, I have force of gravity, normal force, and then let's say this is Ftx, Fty, right? And in this, we have normal force, Ft as well, pointing in the same direction, and then Fg, right? So you're just trying to figure out which one has the largest normal force. So you can kind of see that by looking at, okay, well, normal force is looking in the y direction, right? We're concerned only with the y direction forces. So we don't care that there's an x component to tension here. We don't care that there's an x component to tension here, right? So if we can set up Fnet equations, we can see that, okay, for the first one, Fn minus mg, and we're assuming that this doesn't move in the y direction, right? So Fn should equal mg, since it equals 0, right? So Fn, let me actually write that out. Fn minus Fg is equal to 0, so Fn equals Fg for the first box, right? If we draw an Fnet, or write down an Fnet for the second one, we see that there's Fn plus Fty minus Fg, right? And then for the third one, we see that Fnet is equal to Fn plus Ft minus Fg, right? And those are also equal to 0 here, right? So we want to see what Fn looks like. How does it relate to all the other values? So we know for the first box, Fn is equal to Fg. How about the second box? Fn is equal to what? Fg minus Fty. And for the third box, Fn is equal to Fg minus Ft, right? Now, the idea here is that you have to notice that this one, for the third box, is the full 10 newtons for the tension force. Fty is not going to be the full 10 newtons, because if we were to use like trig, for example, if we were given an angle, right? This is our hypotenuse, so this is the longest side. This would be the full 10 newtons. This might only be like 7 or 8, for example. So we can think about this as being like Fty is like 8 newtons, and Ft here is 10 newtons. So this would be 10, 8, for example, right? So we can see here that Fn is equal to Fg. Here, Fn is equal to Fg minus something. So let's say that Fn is equal to Fg. Let's say that's Fg is 30, for example, right? I just like to throw in values here to make things a little bit easier to understand. So if we have Fg is equal to 30, then 30 minus, let's say, like 8, right? That's going to be 22. So this is 22, for example. Well, 30 minus 10 here, right, is then 20. Right? And so you can see there that, okay, well, if the first one is equal to 30, the second one is equal to 22, and the third one is equal to 20, then the first one is greater than the second one, then the third one. So you see that here, Fn is getting the full value of gravity for the first box. Fn is getting only a little bit of the force of gravity, right? It's not equal to that full 30 newtons, for example. It's equal to a little bit under that, right? And then this one is even less. Why? Because once again, this is only part of the 10 newtons, because Fty is only a component of the 10 newtons. Here, you're getting the full brunt of it. Does that make sense for whoever asked that question? I think it was Carlos. Okay, cool. So, any other questions about the multiple choice? 20. So this spherical object with a diameter of 0.2 meters is moving through a fluid with a density of 2,500 kilograms per meter cubed and viscosity of 5 Pascal seconds. What is the smallest speed the object can have such that the drag is purely inertial? So inertial drag is when your Reynolds number is equal to at least 1,000. It's 1,000 or greater up until like 10 to the 5th, I think. So the smallest speed would then be when it's just equal to 1,000. Because Reynolds number for inertial drag, it can go from 1,000 up until 10 to the 5th pascals. Or 10 to the 5th, my bad, not pascals. And so we know that Reynolds number is density of the fluid, that's fancy P, times the length, right, times the speed, and then that's over what? I forgot. That's viscosity. Yeah, that's equal to your Reynolds number. So we can set that equal to 1,000, right? We have density of the fluid is what? 2,500 kilograms per meter cubed. We have the length is 0.2 meters, right? When we're looking at length, right, the length of a sphere would just technically be its diameter, right? The whole length of that sphere. If we were to do like a cross-sectional area, that sphere length would be the diameter. And so you just take 0.2 and then times your speed and divide by your viscosity, which is 5 Pascal seconds. 5 times 1,000, 5,000, right? And then you can use that to kind of figure out your speed there. Does that make sense? Yep. Any other questions about the multiple choice, or do you guys think you want to look at some of the written problems? I got it. That equation, yeah, it should be given. Like almost all your equations would be given. Yeah. even like volumes of spheres and stuff like that, like you'll have everything you need for the equations. You literally don't have to memorize any equations. Yeah. I remember the days where I had to memorize the equations for AP Physics, and that was not good. Yeah. Oh, now you're getting good. Fancy N is viscosity. Yeah. You got to say it before I did. Yeah. Fancy N is viscosity. Nice. You're learning. Yeah, the equations were on the sheet for AP Physics. I'm just talking about like my classroom exams. They never gave us equation sheets. So like I had to like walk in and like know all the kinematic equations by heart. What else? We never got to fluid, so that wasn't a problem. But yeah, just there were a couple things. Oh, we did like electricity and magnetism. That was I like electricity. So it's not horrible, but yeah, here's what it is. Yeah, and I do have to memorize it for the MCAT. So yeah, but all right. So I think that's probably it for most of you guys. It seems for the multiple choice section. You can see that it's a lot of just concept stuff, really, hopefully, like to a certain extent, a little bit more straightforward than like your average written homework problem. It's very like quick, like conceptual stuff, like plug and chug, hopefully. So, hopefully, you guys didn't find it like too horrible, I guess. I mean, I know for sure, like some of these, especially like out of all the problems, I hate this one the most because this one took me like a hot minute to figure out. But otherwise, I mean, do you guys have any specific problems that you guys want to go over? I know someone had requested to go over like problem 4 parts E through G, I think, or well, I don't see a G, E through G on my end, but um, I don't know. Do you guys have different problems? Hold up, is this the same problem that you guys have for problem 4? Oh, that's not good. Is it a totally different problem? Is it Oh, it's about springs. Um, well, oh well, that's not good. How about 5? Does that look familiar at all? Okay. 5 is cool, so 4 is a problem. And how about 3? Pushing and pulling. Nope. Oh wow. Oh, so you guys had 2 spring problems? So your 3 is pushing. So is your 3 my 4? Wait. Oh, the problems went from 2 to 4. There wasn't a 3. Whoa. Okay. Okay. I should have just made sure to like download like the latest um practice exam because like they haven't changed it for like a while, so I just assumed that it would just be the same. To be honest. Um. Oh, it's not racing cars either. Okay, is graphing a bicycle race at least the same? 1 in 5, and you said Jonathan said 3 is yeah. Whoever made this did not check the numbers. Okay, how about I just take a second here to um, get the latest version because I think at this point it's just going to be too confusing. 1 second here. Oh my gosh. Okay. So I think they actually, what they did is, at least I think, I'm not 100% sure, but it looks like to me that they might have taken some of our old practice, like my practice problems, and Let me go through that real quick. Practice exams, or no, it was midterm solutions. Which one is it? Yeah, this one. Yeah, so this was my actual exam that I took. And I'll upload this to Google Drive so you guys have this exam as well. But I want to say, yeah, that's what they did. So they took our problems. You guys can't see my screen? Okay, cool. Yeah, so you can, this is, yeah. So this is my actual exam. So my exam is what they used for your guys' yeah, okay, I see. Oh, but they didn't use number 5. I took the class, how long was this ago? Okay. So I took 132 last semester, so it was last fall then. So fall, 2021. Yeah. Yeah, I mean I'm like relatively recent. I started peer leading for 131 like the semester after I took it. So last semester was, well, not really old. I'm 19, so I'm probably still younger than a decent amount of people here. So yeah, birthday's in a couple weeks, so woo. um, but yeah, number 5 is, yeah, I'm a junior. But yeah, so number 5 was the sinking toaster. This one was just ridiculous to solve because we got like 18.9 millinewtons for some of these, and we were like, everyone just so thrown off, because it was a comically tiny toaster. So like everyone was going back and changing their answers, and so like everyone got problem 5 just messed up. So yeah, I guess I am a young junior, and yeah, that is a baby toaster. But okay, I mean, considering that this is the actual, yeah, okay, hold up, they'd like is okay. No, the first one you guys already said was the biking one, so I guess they just took 2 and 3 from my exam, or 2, 3, and 4. I'm guessing. Yeah. Yeah. So with these problems, all right, which one do you guys want to go over? I guess. Which one is giving y'all trouble? So there's number 5 and okay, hold up. 2C. So we have 2C, 2C3, go over vectors. Okay. All right, shoot. I was hoping for there to be some kind of consensus. But okay, let me stop sharing and then reshare here real quick so you guys can see properly. 1 second. Okay, is that better? Okay, cool. I don't know why it kind of blurs, but someone said 2C. I have a request for 5 as well, and 3. 5, I'll just have to jump back to the other one here. I think 5 was the first request. Do you have a specific problem with 5? Like, is there a specific part that you're having trouble with? Because I just have the answer key for this. I don't have a blank sheet, unfortunately. So I can just kind of like explain something to kind of pinpoint an issue with it. Did you just do a miscalculation or something like that, or? Part D, okay. So part D is determine the density of the unknown fluid, okay. So since bacterium is moving at a constant velocity, acceleration, hence net force must be 0. Okay. So we have, what is it? Buoyancy force, viscous drag pointing upwards, and then gravity pointing downwards, right? Now, if you've already figured out your drag force, right, and your, I think they gave you buoyancy, is that right? Or did they not give you buoyancy? I'm just going back and checking through the problem. They had 16 times 10 to the negative 15 newtons for the buoyancy here. I'm just trying to look for how they came up with that. Oh, I see, my bad. There. My bad. Okay, so for part D here, you're gonna want to set up a net force equation in the y direction, right? So you have your forces in the y direction, FB pointing upwards, FV pointing upwards, and FG pointing downwards. So the way you would set it up is FB, so F net y, is equal to FB plus FV minus FG, right? And then that's equal to 0 because this thing is what? I think they said it was floating. It's sinking through an unknown fluid, okay. Drag is viscous. And, okay. Yeah, they said it was moving with constant velocity. Yeah, and it's because they said it would reach the terminal speed. So terminal speed is just going to be the final speed that it reaches. It's the maximum speed. It's going to continue moving on with that speed. And so if it's now moving at its terminal speed, it's moving at a constant speed pretty much forever at that point. And so your net force then would be 0 because if you're moving at a constant velocity or a constant speed, acceleration is 0. And so you have F net is equal to 0. So then you can set up this equation, set it equal to 0, and then you have FB is equal to FG minus FV, right? And then you have your FG from the earlier part and your F drag, which is your viscous drag from the earlier part as well. You subtract those two, you get a force of buoyancy. And then from the force of buoyancy here, you can set that equal to, once again, when you're talking about force of buoyancy, we're only talking about things or values that are pertinent to the characteristics or properties of the fluid itself. So we're looking at density of the fluid, volume of the fluid displaced, and gravity. So you have now the force of buoyancy, and that's going to be set equal to the density of the fluid times the volume displaced times the gravity. Volume displaced was the 4.2 times 10 to the negative 18 meters cubed. And I think, yeah, that was given here in the problem. Yep. And then your gravity, divide by that, 10 meters per second squared, and that should give you your density of the unknown fluid. Does that kind of clear it up there? Gotcha. Okay. No worries. But yeah, that's 5D, that was, right? And someone had asked about 2C earlier. No, actually, well, I have to switch back to the other one. So 2C, vectors. So it says what? Consider vector C is equal to 2A minus B. Compute the magnitude and direction of C. Give the direction as an angle from an axis which you specify. Okay. So when you're doing your vector addition, vector subtraction stuff, right? So when you subtract a value, like B here, for example, all that means is that you're adding the inverse of it, or adding the opposite to it, right? And then when you're multiplying by this coefficient, it just means you're doubling the length of the vector. So if we're going for 2A, A we have is a certain length, right? We double it, that gives us 2A. And we have B here is 30 degrees south of east, right? So then its inverse would just literally just be flipped over this way, right? And so that would be, since these were technically this angle right here and this angle right here, those are like vertical angles, they should be the same. So even if you don't know the geometry kind of reasoning for that, you can think of, okay, well, if I'm going 30 degrees south of east, I should be then going, for the inverse, 30 degrees west of north. Because if I were to draw kind of like a makeshift little coordinate plane here, right? If this was 30 degrees south of east, this should be 30 degrees west of north. So south of east, right? West of north. So you can see here that the directions are kind of flipped. East, west, south, north. See what I mean? So, once we kind of have that set up here, 2a minus b, let me take a look at what they had. So you already figured out what bx and by are from an earlier part, right? So that gives you your bx component, by component here, right? So that means that your 2a here is going to be added to by to give you the total y value of cy, and then your bx here is just going to give you how far cx is, because the original vector, which is a, was only in the y direction, right? So in that case, you can see here that cx, they just do 2ax minus bx, right? 2ax is just going to be 0 because there's no x component to a at all, right? So it should just be equal to bx, right? Like I said, it's just only in the x direction for b. Bx should equal cx at that point, and it should be a negative 4.33 centimeters because you're going west or in the negative x direction. Cy should be 2ay minus by, or in other words, right, it should just be 2a plus your component for by. So for by, you had negative 2.5 centimeters because initially by was in the negative direction. Now you have to flip it. Now it's in the positive y direction. So now it's going to be a positive 2.5 centimeters. So I look at what's the length of a, double it, and then add positive by to it, the opposite of the original. So then 2ay, a was what? Ay was 5 centimeters, so that's 5 plus 5, that's 10 centimeters, right? And then I add that to positive 2.5, that gives me 12.5 centimeters. So now that I have a cx and a cy, cx, right, and a cy, then I can do Pythagorean theorem. A squared plus b squared is equal to c squared. In this case, your a squared, right, plus b squared, that's kind of saying like your cx squared plus cy squared. And then your c squared is actually like the overall vector c. And so if you take the square root, you should be able to get square root of cx squared plus cy squared should give you what the value is for the vector c. And that should give you 13.2 centimeters, right? And then after that, right, from those values, right, if you have cx and you have cy, right, you can then use some trigonometry to figure out what the angle is here, because we need to define this angle, right? So you can take tangent, inverse tangent of x over y, right? And I think, actually, hold up. That's kind of weird. Oh, I see what they did. So they did cx, cy like that. And so they did, or I wrote cy twice, my bad. Cx, cy like this. And your tangent is opposite over adjacent. So this is the angle here. This is opposite, and this is adjacent to the angle. So they did inverse tangent of cx divided by cy. And that gives you the angle right here. That's going to be the angle west of north, right? Now you could also take inverse tangent of cy divided by cx, cy over cx, inverse tangent of that, and that would give you this angle right here. And so that would be what? North of west. So you have west here, and you go north of it to get this angle. And so west of north is this angle right here. North of west is that other angle right there. And so if you wanted to find the other angle, it would just be literally 90 minus this one, right? That's like 70.9, I think. Yeah. So 79.9 degrees north of west as well. Either way works. You just have to make sure that your angle matches up with the inverse tangent values that you're calculating. So if you do cy over cx, you get this angle, and that's north of west. If you do cx over cy for your inverse tangent, you get this angle, and that's west of north. Does that make sense for 2c? I can't remember who asked that, but hopefully that makes sense. Cool. Let me scroll up a bit and see 2c. Jonathan, I think you had 3 as well. So is there a specific part to 3 or just in general? Because this, when I was talking about, I don't know if you've watched my sessions or if any of you guys will watch my sessions, but number 3 is what I was talking about in that one written homework where I was saying like the double box problems are literally my nightmare, because this is exactly what I got on my exam, and my goofy little self just blanked out on how to draw a free body diagram for block A and block B. So now I understand it though. So that's where I'm there to help. Yeah. It's good though, because like I feel like this semester is a little bit easier than the last semester. That's actually a bit easier, because I feel, considering the fact that they've given you some of my old exam problems as your practice exam, and the fact that these quizzes that have been given to you guys have been very similar to like what my quizzes have been. Hopefully the exam that you guys get is decent, because I remember the exam that the students got last semester was just a little bit iffy sometimes for some of the questions, but yeah. Yeah, Jonathan, is there a specific one that you want to go over for 3? The whole thing? Sure, that's fine, no worries. Before I go and do the whole thing though, because I want to make sure, like, because this is going to take time. This is like parts A through G. So, well, I guess someone had asked for E through G, I think, before. But yeah, I mean, do you guys want to? Does everyone have a consensus as to go and do problem 3, or are there any requests for like smaller parts or something that we can maybe get out of the way quicker? Just because I want to make sure that we're doing like as much as possible. Okay, I'm seeing one person. Well, 2 people, I guess, technically. So, okay, 3. Let's do 3, I guess. Okay, no worries. So, pushing blocks. Consider 2 blocks stacked one on top of the other. As shown, a person exerts a pushing force, F push, with a magnitude of 15 newtons on the block. Force is directed at an angle theta is equal to 40 degrees from the vertical. And the 2 blocks slide together, and they each have a mass of 3 kilograms. Coefficient of friction between the lower block and the surface below is 0.2. So they want us to draw a free body diagram for the object O, and that's both blocks together, right? Both blocks together. So when we're drawing this, we're not concerned about each individual perspective of the box. It's just the whole thing, right? So A and B together will pull downwards, basically. They will both, their weights together will pull downwards with a force of gravity, right? That's going to be our first force that we can draw there on our free body diagram. And then, based on that total force of gravity, we have kind of like a combined normal force, right? Pointing upwards. Now, they also mentioned friction. It's a rough surface, right? And if we're trying to push this way, right, this pushing force is directed at an angle, so you have a F push X, basically, and an F push Y, right? Now, considering that this block is just sliding across the floor, you also have to keep in mind that, well, there shouldn't be any net force in the Y direction. This block isn't levitating, it's not sinking through the floor. We want to make sure that the Y components are adding up to each other in a sense that Fn minus Fg minus F push Y all add up to 0. So we can try and draw that to the best of our abilities that they're equal to each other, or that they cancel out, essentially. So like, if you think about it, F push Y, if I were to add that to the length of Fg So it would kind of look like maybe like this. I should maybe draw my normal force a little bit longer or something. Here they just kind of, it is what it is. They just kind of drew it there just for the sake of space and the answer key and whatnot. But try as best as you can to draw things proportional to what makes sense in the problem. But yeah, we should have FKX opposing our motion, because if we're moving to the right with our F push X is pushing us to the right, then this thing should, or my bad, not to the right, to the left, my bad. And so if you're trying to move to the left, kinetic friction will oppose you to the right. So those should be your forces acting overall on the whole object system for your free body diagram. Does that make sense for part A? Cool. Now, for computing the magnitude of the normal force from the surface on the combined object, right? That is factoring in the key thing that I was talking about earlier, right? That this object is not sinking, it's not levitating, so we should have an F net Y of 0, right? So the forces that are going to be factored in here are the normal force of the combined system, Fg of the combined system, so this Fg should be factoring in both weights of both blocks, right? And then we have F push Y as well. So we can set up an F net equation, right? F net equation, F net Y is equal to Fny. And I don't like how they put plus for everything. So when I set it up, I would do this on the exam. I would say F net Y is equal to 0, because I know this isn't, there are no net forces in the Y direction. And so Fny minus Fgy minus F push Y. Right? That's how I would set it up. And so therefore, my Fn is equal to Fg plus F push Y. In that case, that's how I would set mine up, right? And so you can get your F push force, right, by taking that push force that I think they gave you, right? They have 50 newtons, right? So this force here is 50 newtons. We can use trig, specifically cosine. So if this was cosine, what was the angle? 40. So we can do 50 cosine 40 to figure out what F push Y is, right? Once we have that, that's going to be that 38.3 newtons that they gave you here. The reason why they have negative here, right, is because they didn't integrate direction directly into the problem. So they have to assign a negative and then plug that negative back in, because that way you can see if they have a negative 38.3 that they plug back in, they can add it and it becomes positive 38.3 on the left hand side. And so I just did Fny minus Fgy minus F push Y, so that I can just put in the magnitude 38.3 and I add that over, and that's automatically 38.3 right there. So I know that Fn is equal to Fg plus 38.3 for F push Y, right? And so then you have this Fg here. That's going to be the combined force of gravity, right? And so, where is it? I totally lost my train of thought. You would, no, for some reason I just totally got lost there for a second. Yeah, I was thinking about the two blocks together, right? Those are each 3 kilograms. So 3 plus 3, 6 kilograms, 6 kilograms times 10 meters per second squared is going to give you an overall 60 Newton force for a combined force of gravity that factors in the weight of both boxes. That's where they're getting this 60 newtons here. So it should be 60 newtons, right? Plus your F push Y, which was 38.3, and that should give you 98.3 for your Fn, your normal force. Does that make sense for part B? So you set up a F net equation, should be equal to 0 because there's no motion in the Y direction. Set it up like this, right? I like to integrate the directions, so then I can just add everything normally on the left-hand side, so Fgy plus F push Y. Fg here is the combined weight of both boxes, so that's 3 kilograms plus 3 kilograms. That's 6 kilograms total for my mass. Fg is equal to mg, so 6 kilograms times 10 meters per second squared, that's 60 newtons. 60 newtons, plus my F push Y, which I already said I can figure that out using trig, because 50 newtons here is the force that they gave us. I can do 50 cosine 40, which is the angle, to get F push Y. And then you just kind of add them up, and that's how you get your normal force. Now for C, they're asking you to compute the magnitude of the friction force from the surface on the object, right? So we know that the friction force here, since the box is sliding, it's not static, right? It's going to be kinetic because it's sliding, right? And so your kinetic friction force is mu times Fn in this case. So we have mu, the coefficient of friction, times our normal force that we figured out from earlier. So that's a simple plug and chug. You get the coefficient of friction here was 0.2. Multiply that by the normal force, you should get your kinetic friction. Sound good? Cool. Part D, compute the magnitude of the acceleration of the combined object, right? So, once again, we're interested, when we're looking at it, since there's a net force to the left, this box is being pushed to the left, we're concerned now with the F net x forces, F net x, right? So there has to be some kind of acceleration in the negative x direction, right? In this case, because it's moving to the left, that would give us a net force to the left, right? So the forces that are concerned in the x direction are F push x, the x component of the F push force, and kinetic friction. Once again, I don't like adding everything up. I like to integrate the direction. So I know F push x is actually negative, right? And so let me actually do it this way. So I know that Fk prime is opposing my movement to the left, so that's positive, and then minus F push x, which is negative, right? And that's equal to my F net x, and that's equal to max here. So once again, I can figure out F push x using trig, because I had the 50 newtons from earlier, 50 newtons. So 50 sine 40, I get the opposite over the hypotenuse, right? So 50 sine 40 is going to give me my F push x, right? And I can plug that in. So F push x, they gave you 32.1 newtons. I've already integrated the direction, so all I have to put is 32.1, and the minus sign is already there, right? And my Fk prime, well, I already figured that earlier, which is 19.7, right? So I just take 19.7 minus 32.1, and that should give me like the negative 12.4 that they have here, right? And so if I take negative 12.4, since this was equal to max, right? This was all equal to max because there's an F net, there's a net force to the left. Then if this was negative 12.4, and this was 6 kilograms, right? Because this is the combined object still. We're looking at the acceleration of the combined object. So we just divide over 6. That should give us around like negative 2 meters per second squared for the acceleration in the x direction, right? And now they're asking for the magnitude. So we know that there's a net force in the negative x direction. So it makes sense for us to have a negative acceleration. However, they're asking us just for the magnitude. And whenever they ask you for the magnitude, just take the absolute value. So if you end up with a negative number, assuming you did everything else correctly, and they're asking you for the magnitude, just take the absolute value. So absolute value of negative 2.07 is equal to 2.07. So I wouldn't even, this is just extraneous. This is just additional, like you really don't have to do it because you already know that there's no acceleration in the y direction. So it doesn't make sense for you to do, 2.07 squared plus 0 squared, and take the square root of that. Well, that's just going to be 2.07. You're just back where you started. So this doesn't make any sense. You already have your acceleration here. Just take the absolute value of that, and that gives you the magnitude of the acceleration. We good for D? Cool. Alrighty. E now is where I screwed up big time. This is where I lost like a majority of my point. Like I think I missed only one multiple choice question and like 3 points alone on this damn question. So there you go. The only issue with physics is that I make stupid mistakes. Mostly. That's mostly my only problem. But we have draw 2 free body diagrams below, one for block A, one for block B. Label all your forces with explicit superscripts. I think that's where I went wrong too, the superscript part. In the superscripts, use E for Earth, S for the surface, and P for the person. So whenever you're drawing individual free body diagrams like this, right? Especially when you have this frickin' 2-box problem, you have to keep in mind that you're drawing your free body diagrams based on the perspective of each box. You only draw what each box feels, right? If box A, let's say, okay, for example, let's say this, right? I used this example when I was doing the written homework a couple weeks ago. Let's say, I don't know, person 1 is standing in line, person 2 is standing in line, person 3 is standing in line, right? Let's say person 1 felt a push force. They pushed person 2, right? Then person 2 pushed into person 3, which is me, right? Now, sure, person 1 might have applied that push force, and so now when person 2 comes into person 3, we're both feeling that like combined acceleration, right? We're both feeling that combined acceleration. But when it comes to what forces we feel, I'm not going to be feeling person 1's hand. I'm just going to be feeling the force of person 2's body on person 3 here, right? So imagine this is me, person 3, right? I don't feel that person 1's hand is acting a force on me, right? I just feel that person 2 did, for example. So I only draw the forces that pertain to me, to pertain to what I feel. Now, person 2 is kind of unique because not only do they feel the hand that's pushing on them for person 1, but they also feel me, right? Because I am standing there and they bumped into me. So they're getting hit by person 1 and then they're getting, I guess, blocked by me because I'm standing there, right? And so that's kind of the idea there where like you have to factor in what forces pertain to each individual object by themselves and what do they feel from their own perspective. So when it comes to block A, right? Block A is on top. Block A is just chilling, right? So block A feels gravity, right? That's natural. Block A feels gravity from the earth on itself, right? That's what it feels, right? Now, block A is also feeling a normal force, but not from the surface. It's feeling a normal force from the contact surface that it's in touch with, right? And that contact surface is B. So it feels a normal force from B on it, from B on A. And it feels gravity from Earth on A, on it, right? Now, we go back here, right? There should also be a static friction force. Why? Think about it. If this is real life, and I'm pushing the blocks stacked on top of each other like this, what prevents this object from like just slipping and sliding and moving all the way around? What makes it so that this object, when I'm pushing them both together, that this stays relatively in touch and static? Static, that's the key word, right? On top of B. That's static friction, right? So, you should have a static friction force from B on A that would prevent that motion, right? Does that make sense? Now, for block B is a little weird because block B feels a lot of different forces on it, right? Remember, block B was on the bottom, A was on the top, right? So block B, first of all, feels force of gravity just from the Earth on itself. Force of gravity, Earth on B, right? Yeah, and you just put what forces each block feels on its own. So block B actually feels a lot because not only is it in contact with the surface, but it's also in contact with block A directly. So like, imagine like if you're, I guess playing with a sibling or something when you were little and they jump on top of you and you're having like a pillow fight or something, right? So if you're on the ground, for example, and they go and attack you, right? Well, you feel that ground like on your back or something, right? So there's a contact force, normal force right there that you feel from the surface or the ground on you. And you also feel kind of the force of your sibling, for example, coming down on you, right? So there should be technically two normal forces, two contact forces that are acting on you. So yeah, normal force, two objects touching each other in the y direction. So that is if they're on top of each other, right? And so in this case, box B, since it's on that surface, on the floor is pushing back on it. That's the normal force of the surface, the floor on the box B. But it also feels a normal force, a contact force, from A on B, right? It feels the pressure that your sibling, that box A is exerting when they're on top of you, right? That's the idea here. So box B is squished in the middle. It's not only feeling the force of the surface, underneath it, but it's also feeling the fact that, oh, well, there's something above me that's pushing on me, right? That's the idea of what it feels. Box B feels squished. It can't sink through the floor because the floor is there. And then box A is just deciding to chill on top of it, right? So it feels pressured. It feels squished. That's the idea. So that's why there's a normal force acting A on B. Obviously, box B is the one that's actually being pushed as well, right? So if you think about it here in the initial part of the problem, they were saying that the push force is applied to block B. And you can see that in the diagram there. So box B is the only one actually feeling the push force. Block A doesn't feel it. Box B is the one that feels the push force. So it feels the, you can say like hand on B, for example, right? Now that takes care of a lot of the forces in the Y direction, right? Now, there should also be some forces in the X direction. So number one, there should be kinetic friction force, right? S on B, the surface on B, right? Because if the box is trying to move to the left, right, there should be a kinetic friction force that opposes its direction to kind of prevent it from sliding. So that makes sense there, kinetic friction from the surface on the block B, because block B is really doing the work. Yeah, right, Jonathan. Block B is doing all the work, trying to keep block A happy, right? So block B is trying to do the sliding against the kinetic friction. Block A is just chilling up there. It doesn't feel any of that kinetic friction. It's not sliding, right? And so there's the kinetic friction from the surface on B. Now, what's really interesting, what threw me off personally, was the fact that there's static friction force is actually an action-reaction pair force. There's static friction force from B on A and A on B. And the reason why that is you think of A kind of gripping onto B, right? A is kind of gripping onto B. So in that sense, right, there should be a static friction force that is felt by both blocks to kind of grip each other, right? Because imagine on a surface, right? Let's say it's a car driving, right, on a road. Well, the car has tires. It has that grippiness to the tire, and coupled with the nature of the road itself, right? The road's kind of a rough surface, so it kind of helps for like a double grip, essentially, right? Now, as soon as you add snow to that equation, there's no longer so much grippy force, quote unquote, from the road. Now, in order to keep the grippiness overall between the two objects, each one basically kind of has to feel that grippiness, if you will, right? So block A feels the grippiness from block B on it. So like that would be like the tires feeling the grippiness of the road. And then at the same time, block B, right, feels the grippiness of the tire on itself, or tire on the road, right? So like block B feels the grippiness of A on itself. So both of them are feeling a grippiness force from each other. The reason why normal force is downward for this one, right, there's two normal forces. Box B is feeling a normal force from the floor that keeps it from sinking through the floor, that's surface on B. And it also feels a normal force. Normal force, remember, is the contact force. A is in contact with B. So normal force here, when it's pointing downwards, is referring to essentially like the weight of A on B. Does that make sense? So normal force is downward in that case, A on B, because A is kind of exerting that pressure on B. It's coming into contact with B, and B is feeling that pressure from A. It's feeling that squishing pressure from A on top of it. Does that make sense? Okay. E is a doozy. Hopefully that kind of cleared things up, especially the static friction part. But yeah. And so for part F now, they're asking you to list all the forces that are action-reaction pairs. Static friction force should be an action-reaction pair because each force is kind of exerting kind of its own grip, right? Box B is exerting a grippy force on A. A feels that. Box A is exerting a grippy force on B. Box B feels that. At the same time, right? Box A is feeling a normal force, right? From B on A. B on A. And box A is exerting a force, normal force, from itself on B. So B feels the pressure from A, and then A feels the pressure from B. Someone asked this same problem, why is FGY equal to negative 60 when mg is 3 kilograms? Yeah, because you're factoring in both boxes. Remember, they wanted to find the combined object's acceleration. So when it's a combined object, you add both masses, 3 kilograms plus 3 kilograms, and that's why you get 60. But does that make sense for E and F there, for the free body diagrams there? But yeah. Now, the trippiest part is G, because essentially box A has to maintain, or has to be at rest on top of B, right? That's for sure. Now, the issue is it also has to move with B, technically. So it has to stay static on top of B, but it also has to move with B because of that push force. And so part G is asking which force helps block A kind of move along, but also stay on top of A. That's what it's asking, essentially. And so the force that is doing that is that static friction force, right? Now, that's why they've kind of drawn one bigger than the other, right? Block A has a little bit more grippiness than block B, and that grippiness helps propel it forward along that negative x-axis to keep in motion with B, moving in the leftward direction as well. But the fact that there even is an existence of a static friction force, right, means that the object is not slipping. So static friction force in and of itself prevents the slippage of A, but it also kind of helps the block grip and move along with B, right? Does that make sense? I know that's a little weird. Like, this is the trippiest problem you'll ever probably see in physics, and it threw me for the loop, and it's, I think, the longest problem I've ever seen in any physics course that I've taken ever. There's just so many parts to it, and EFG were just really trippy. But hopefully that kind of cleared things up. Hopefully the analogies kind of helped you make sense. It's very informal, but I mean, that's just how I like to think about things, and hopefully that kind of helps give you an idea. I don't think they'll like go crazy with this type of stuff. Hopefully, like I feel like they might give you a 2-box problem, but I'd be damned if they give you a problem kind of like this where it's just insane. Especially considering the fact that, like, I don't think they would give you one with the exact same length and exact same look as the one from the practice exam. And just based on personal experience, previous history, practice exam is almost always harder than the actual exam. So if you guys felt decent about this one, like maybe you weren't like the greatest, maybe you didn't feel like you knew all the answers and stuff, that's fine. If you can get your stuff ironed out between today and the exam, right, you're going to be okay. Because in my opinion, the actual exam is just a lot easier for the most part, except for this damn problem. So, yeah, hopefully you guys do well. If you've been coming to the sessions, or at least watching them online, if you've been finding them helpful, you're doing all the hard work, you should be okay. So, it's 8:04. I think that's probably going to be the wrap up for this session. I'm very tired. So, yeah, if this session will be uploaded on YouTube as soon as possible, and I'll upload all the exams that I have access to, because it looks like their practice problems are like all over the place. But yeah, exams are similar to the quizzes. Yeah, I mean, with regards to the quizzes, the written parts are going to be most similar to the quizzes, as well as the written homework. So I make sure to do the written homework, do the quizzes review, and then sprinkle in some online homework. I did send a guide to the professors. I think they posted on Blackboard, and it's also on the Google Drive that shows you exactly what to review, if you have time and if you don't. So if you need to cram, there's a certain amount of things that you have to do. So like go over the slides, for example, go over the written homework and the quizzes, and that's it if you have to cram. But if you have time, you obviously have more time to review other things. So you can do your written homework, your quizzes, your slides, a little bit of the online homework, maybe an extra practice problem here and there, right? But yeah, I sent both of those, or sent that guide in the Google Drive. So hopefully you guys have access to that. And then, yeah, so praying for you guys, and hopefully you guys do well on this upcoming exam. Alrighty, I think we're gonna call that a night.